Hello everyone, I'm Seogu Jang from Anyang University, Korea. Today my talk will be about efficient covering of a target object using a prediction technique. In this presentation, I'll first provide a brief introduction to personal information covering. Then, a learning-based detection of target objects will be discussed. To detect target objects, a skin color model and a deep learning technique will be introduced. After that, I'll talk about covering target objects. To track and cover target objects, a target object model and a position prediction algorithm, as well as a blocking technique will be used. After that, some of the experimental results will be presented to evaluate the performance of the suggested algorithm. Finally, I'll conclude my talk. With the rapid development of the internet and information technology, it has become very easy to access and browse multimedia content on the web, including photographs, movie clips, and music files. On the other hand, various types of image big data, including target objects with exposed personal information, such as naked area of a person, face area, phone number, and home address, can also be easily obtained and distributed through the internet, which becomes a social problem. Therefore, our target object covering system is needed to effectively block this type of image data containing personal information. Most of the previous target object blocking methods are based on human skin region detection. In other words, they first detect skin color regions from input images and then analyze the characteristics of the detected skin regions to block personal information images. Although skin extraction-based methods have been frequently used with its simple algorithm, they are limited to identify all personal information images taken in far different environments just by using skin regions. Some other approaches extract human body parts representing personal information to filter out images but do not have high detection accuracy. To overcome these problems and block personal information effectively, a new target object blocking algorithm is suggested. The suggested method first extracts human skin regions. It then detects facial regions from extracted skin regions by using deep neural computing. And subsequently, the location prediction algorithm is used to quickly track the detected object. A mosaic is overlapped over the target object area to effectively protect the object area where the personal information is exposed. In the following, I'll present the problem of detecting target objects. To extract skin color regions from an input image, the suggested method defines a skin color model. For this purpose, input image's color space is first transformed into YCBCR space, which is known as the most appropriate for skin extraction. Usually, the distribution of skin samples in the CBCR subspace takes the form of an elliptical shape, as shown in this figure. Therefore, elliptical skin color model is used to separate skin pixels from background, and it is specified by the center and spread of the elliptical cluster. After making the elliptical model of skin color distribution, skin segmentation for the test image is performed with the model. In other words, if the color of a pixel in the test image is within the range of the elliptical model, the pixel is defined as a skin color pixel. Otherwise, it is classified as a non-skin color pixels. The proposed method uses a CNN-based deep learning algorithm, which is one of the machine learning methods to accurately detect only the facial region representing personal information from the human skin region extracted in the preceding step. To detect the target object at a high speed in the video, the image is transformed into a pyramid structure in the learning stage. In the proposed deep learning structure, the image pyramid is formed in 6 steps. When an object is detected, each detection result is summed in each step of the pyramid to calculate the final result. At this time, in the image pyramid, level 0 represents the original image and the resolution is downsampled to 1/2n times as the level goes up. The structure of the deep learning model used in this paper is shown in this figure. In this figure, the convolution layer is a layer that extracts features through convolution. In the proposed deep learning algorithm, the activation function uses the rectified linear unit, that is ReLU function, instead of the sigmoid function. In the structure of the proposed deep learning model, the affine layer represents a fully connected layer. Normally, an affine layer is added just before producing the final result at the top output node of the deep learning model. Generally, the affine layer is made in the form of y equal f of wx plus b, where x is the input layer, b is the bias, w is the weight, and f is the nonlinear activation function. In the structure of the proposed CNN model, max margin object detection optimizes all sub-windows without performing subsampling. In other words, the target is detected by applying f of x and y, which is a window scoring function, to all sub-windows. In this function equation, phi is a feature vector obtained from the moving window position r of the image x. W is a weight vector and reduces first detection through learning. Applying this equation in the proposed method makes it possible to obtain the result corresponding to the detection score. Subsequently, the area having the highest score in the pyramid image is summed to extract the final target object detection position. In the following, I'll present the problem of tracking and covering target objects. In this paper, the target object is not detected for every frame of input image. Instead, the efficiency of the proposed system is increased by quickly tracking the target objects using the position prediction algorithm from the next frame based on target object detected initially. In this paper, we used the kernelized correlation filters algorithm that is robust to object shape changes to quickly track the target objects. In this study, features are extracted for the input image, and tracking is performed using all sub-windows through dense sampling, as shown in this figure. In this paper, when personal information is detected from the continuously input image, the image and the location of the personal information are used to conduct learning of the target object for tracking. The learning proceeds as in this equation, where x is the learning image, that is the current frame, and y represents the target object. Gamma lambda is a parameter to prevent overfitting. In the proposed method, the target object is tracked in the image entered next using the model alpha of the target object obtained by learning. In this equation, k bar is a vector of the element ki bar and corner correlation between the learning image x and the input image z. Y hat is the response vector at all positions. In addition, the position with the maximum value in the final response map becomes the tracking coordinate where the next object is located. The proposed method creates a grid type mosaic and then covers the target object area so that it is not exposed to the outside by naturally overlapping the mosaic created in the previous step over the extracted target area. The proposed method acquires the minimum inclusion rectangle of the object area extracted first to overlap the target area containing personal information with mosaic. Subsequently, the corresponding area of the image contained within the acquired MER is divided into equal block units of n by n pixels in horizontal and vertical sizes, and then each block is filled with values produced by a mosaic processing technique. From now on, I'll present some of the experimental results. The proposed target object blocking algorithm was implemented by using Visual C++ and was applied to various types of images. To construct test image database, various images with faces were used, which were captured in natural environment where specific constraints are not imposed on. To evaluate the performance of the suggested blocking algorithm, two methods are compared, that is, skin color based method and the suggested method. This slide shows some results of blocking target regions with the suggested algorithm. This figure shows an input image, and this figure shows the extracted skin pixels, and this figure shows the detected facial region, and this figure shows a mosaic-based covering result. This slide shows some results of tracking and blocking facial regions with the suggested algorithm. As you can see from this figure, this facial area is being tracked, and this figure shows the facial region tracking and covering. To evaluate the performance of target blocking quantitatively, the accuracy measure is defined like this equation. This figure shows performance comparison in graphs. As you can see, the proposed method has higher accuracy than the other algorithm. Now we'll conclude my talk. In conclusion, I propose the method of robustly detecting target objects with exposed personal information from various types of color images entered using a CNN-based deep learning algorithm and efficiently covering the detected target object using a location prediction-based tracking algorithm. In the future, we plan to I plan to verify the robustness of the proposed algorithm more systematically by applying the target object covering algorithm based on the tracking strategy introduced in this paper to color images taken in various types of indoor and outdoor environments without restrictions. That's all. Thank you for your attention. Thank you.